All right. Hello, everyone. Um, Hello to all the people online. Welcome to the 10th recitation of this course. So today we're going to talk about attention and possible ways to look at the problem of machine translation, which you will be building a language model for in homework 4. All right. Well, it has echo in here, which I'm not used to. All right. Anyways, so modeling language, especially given in the context of machine translation, is can be thought of as a sequence-to-sequence problem, right? So what that means is that a sequence goes in and the sequence comes out, and there is no strict correspondence between what comes in and what comes out in terms of time synchrony or any formal relation of that sort. So you know they may not even maintain the same order of symbols. So for example, if you translate English to French, I mean, that's what the classic example is, at least in the attention paper. But then, we have a German example out here. If you translate I ate an apple into German, then, the resulting sentence doesn't have the same order of, correspondence of sequences as in the English sentence, right? It's like the word apple or the word, ate is it happens somewhere else. So like semantic information can be carried in different locations in the target than in the input. All right. So here is what we can think in terms of inventing a model that tackles this problem. So we tend to think of language modeling as a recurrent task, right? And the reason is that we don't know how long the input is going to be. So there is no way for us to invent, a naive model where you can no longer do what you did in homework 1, where you just make an MLP that takes in a predefined length of input, right? Because then, as we said, there's no fixed length of what the input might be. So then we use a current model. We try to encode all the information in what we've seen in the language input up to the certain point in a hidden state, and then we just recurrently decode this hidden state to give us the information that we want. All right. So to put it formally, the professor should have talked a bit about this info, but then this is for formalization of what we're looking at. So the input that we put into the model is going to be a naive way to think about it is one-hot vectors, right? So if you have like 10 words in your vocabulary, then a very straightforward way to think of the input is this. Literally, it's going to be a vector of 10 numbers, and then if you have, say, a word in there that is present in the input, then you just mark 1 on that index of the input vector. All right, so that's what's called a one-hot vector. And then in the network, what you find is that these one-hot vectors can be projected into lower dimensional, what's called embeddings. So on the topic of embeddings, I mean, embeddings is a pretty interesting thing. Outside of the context of these language models, I find that for just understanding embeddings in general, you can look at what's called word2vec. That's one of the that's one of the earliest deep learning, or not even deep learning, but then semantic embeddings that is interesting in that it's not one hot. It actually embodies the semantic information buried in some of the tokens. And that's a very interesting paper. And there are a lot of YouTube lectures on it. You can just look it up. So Word2Vec is a successful example of what an embedding is. And then so what happens with these models is that they will also map your input vectors to embeddings. And the hidden units that these embeddings get put up to, we can use LSTM units, which are basically gated RNN units, right? So they are RNN units, but with some gating mechanism to prevent the gradient exploding and vanishing and the long-term correspondence memorizing problems. All these problems that we see in RNN, they can more or less be solved or confronted with the LSTM gating mechanisms, right? So we put those, we put the embeddings to the LSTM units, and then this computational graph should be pretty familiar to y'all by now, right? So the W1 would be just the first token, and then you pass it to form an embedding, and then the blue box on the left, it's just the initial hidden state, right? So you combine that with some sort of, basically matrix multiplication and some activation to form the green box, which is the hidden state for this time step. And then you decode that hidden state to give us some sort of output. And then, but we also combine it with the next time step input to form the next step hidden state. So then this is the recurrent structure. I mean, this is a pretty old story. So I'll move on. So, but then the message in here is that this is what a language model, canonically, what a language model looks like. All right. So a couple of formalities again. So in order for us to know when to stop decoding an input, right? Because this thing can go on forever. If you look at this, there's no strict way other than, manually imposing a limit on how many or how many tokens we can have. There is no way of knowing that the output should end at a certain time step. So then what we do is we introduce two special tokens, SOS and EOS. So the thing is, SOS, it literally means start of sentence, and EOS would be end of sentence. I mean, what do the last S mean sentence? I mean, it could be, utterance, it could be, segment, whatever, right? So the thing is, these tokens will be added to your vocabulary and they're treated as just like regular tokens. And then the EOS will literally mean the sentence should end here, right? So whenever you have training instances, you would just like, for each segment or for each utterance, you will prepend an SOS and you will append an EOS and feed it to the model. So the model will know that, generally when you complete a sentence, then the EOS follows, right? So when remember that in each time step in here, the W2, W3 on the top, right? So these are probability distributions, right? So these are distributions on, which tokens should appear here at what probability. So the EOS will hopefully appear with high probability in the output distribution near a later time step. So then when you decode that from the output distribution, you know that the output ends here, right? So if you're on Hugging Face, and if you look at language models, literally any language model, like BERT, like GPT, like, BlenderBot, there are a lot of language models. So these things, they might go by different names. So the SOS, I know that in BlenderBot, which I've been working with lately, the SOS is literally just a square bracket S, and then the EOS would be this, right? So I'm not sure if this can be seen correctly, but then this is, so the point I'm trying to make here is that a lot of, if you go on Hugging Face and you're trying to use some of those language models, especially for your project, then these things go by different names, right? They might not just be, verbatim SOS or EOS. They might be different, but then you just look at the model card and then you can figure out they're the same thing. The functionality is the same. They indicate the start and end of an utterance. The name might be different. Okay. So here are more examples of what these things look like. So this is literally, a small augmentation or like a small addition to the segments that we have. So we append SOS and append EOS to the start and end respectively. Okay. So here, our problem is that we want a good language model to tackle the problem of, say machine translation, which is a language problem, right? But then there is no synchrony between input and output, meaning that there is no correspondence between an input token and an output token, right? So let's give you an example. So if I take this example, I mean, this might not even be the greatest example because I ate an apple and each have an item. So the I in the input sequence happens to correspond to the ich in the output sequence, which are both the first token, right? But then this might not always be the case. So for example, if I say, look, if I say I read a book, right, and I want to translate that to Russian, okay? I say that because I happen to have taken Russian. So I know that there is a way in Russian to say that I read a book in the way that you put the word book first, right? So you would say книгу читаю. But then книгу actually means book, right? But then in English, you would say I read book. So then if you only look at the first, so okay, so if you want to translate I read a book to the Russian sentence as I said, let's say the ground truth is that we want книгу читаю, right? But then, okay, so those are two Russian tokens, okay? But then if you only look at the first time step, if you only look at the first token in the English sentence, there's no way you could output the Russian token. That's the first token, right? Because you haven't even got to books yet. So there's no way you would know that the correct Russian translation would have books as the first token, right? So
Is that because we only see I?
yes, that's because in the English sentence we only have I yet, and so there's no way for us to know that the you know that like there's no way for us to know that we should say books. Like why in the world there are so many things why say books? So we only know that when we get to the later part of the input sequence. But then that's not possible during the first part. So that is the reason why we cannot have synchrony between input and output in language tasks, right? We don't have that property. So so the problem becomes how are we supposed to map an entire input sequence to an entire output sequence? But then knowing that we cannot output each token at a time step, right? We cannot do that because the reason I just described, there's no way for us to know what the complete output should look like before we get the complete input, right? There's no way to know the output token to output with an incomplete input sequence because it might be missing information that might influence our choices for the output tokens. So what we do in this context, so this is what's described as a delayed sequence to sequence problem, right? So we go through the entire input sequence and then we try to map the output sequence, right? So the solution is that, I mean, this is pretty, I'm not sure if this has been covered in lecture so far, but the idea is that we map the entire input sequence to a vector or to a hidden state, right? And we use that hidden state to decode the entire output sequence, okay? So the hidden state will be a very high dimensional vector. It will basically be a vector in a space that is as high dimension as your one of your intermediary layers, and that's going to be very high dimension. So, and the hope is that the hidden state is rich enough, it's expressive enough to contain the entire information in all the in the entire input sequence. So ideally, each possible input sequence will map to a different hidden state. And the hidden state will be expressive enough to contain all that information, meaning that similar input sequences will map to similar hidden states. Different input sequences will map to different hidden states, right? And the hidden state will, since it has all the information, we will just decode it with a different decoder than the encoder. We'll decode it to give us the desired output sequence, right? So you can in this context you can think that the input and output. Let's say we're doing the canonical task of translating from English to French, right? So the encoder it will encode English sentences to this hidden state, and the decoder it will decode this hidden state in the French way, right? It will interpret this in the French way, but then the hidden state itself is independent of languages, right? The hidden state itself is just an embedding in high dimensional space that can be decoded in whatever language. If you have a decoder for Chinese, then you have the Chinese output sequence. That means the same thing because the hidden state itself is supposed to be independent of languages, right? It's just a vector that carries all those meanings. Okay, so here's how to formalize this. The input sequence feeds into a recurrent structure and then is terminated by an explicit end of sequence symbol. So when the input reads the EOS, then you know that the input has ended, right? And then we use a second RNN and use that as the initial hidden state to start decoding the output sequence. And then when the output sequence, when the decoder outputs an EOS, we know that the decoder has ended its the decoding. Okay, so we have two RNNs in there. The first RNN is for the encoding, and the second RNN is for the decoding. And we put them together, and the only thing that connects in between is the hidden state, right? And so you might notice that in the picture in the diagram we only draw one level of hidden states here, but then there's no reason why we would only use one of them. We could have an array of hidden states, right? This is arbitrary. So the point is that we don't. So since we cannot start decoding until we get to the complete input, we condense the entire input sequence in one of those hidden states, right? And then we start decoding. Okay, so this is what's called an encoder-decoder architecture. So I'm sure you've heard about this now, encoder-decoder. So right now, the reason why it's called that should be pretty clear. The encoder encodes, like it's called the encoder literally because it encodes the input sequence to like a hidden state, and the decoder just goes from that. Okay, so here in the lecture, the professor sort of mentioned that at each time step, what the model outputs, what an RNN model or sequential model outputs, is not an independent token, but a probability distribution, right? So if you look at the diagram on the right there, in the first time step of decoding, the different tokens of the German language appear at different probabilities, right? So it's only up to the model to select one model out of these different probabilities. So, there are multiple ways to select a token out of all these possible tokens, right? So, a straightforward, the most naive way you would think is to just select a token with the highest probability, right? So if let's say if each has probability zero point 0.3 and each of all the other tokens will have probability 0.01, so then we would just select each, right? It's a very straightforward choice. So then there's a slight problem with it. This is like slightly off topic, but I find it interesting, and then it's relevant to this use case here, so I thought I would talk about it. So it turns out that you cannot always select the highest probability token. And the reason is that if you do it, if you do this time step by time step, then this can actually give you the suboptimal outcome, right? Because that is basically a greedy search, right? And greedy search doesn't give you the optimal outcome. So for example, okay, I can't write here because it's too narrow, you can see it, but then I can just describe it. Okay, so let's say we're decoding the sequence, and the sequence reads Carnegie Mellon University is in, and then blank, we're trying to decode here, right? Is in what? So, you know, um, let's say the token Pennsylvania, let's say it's a token, and it comes in the probability distribution with probability, let's say 0.3, right? And let's say New York comes in with probability 0.2. And let's say New Jersey comes also with probability 0.2. So what you see at that time step is that Pennsylvania comes in at 0.3, but the word new comes in at 0.4.
New?
Yes, because New York and New Jersey both carry 0.2, right? So if you select the highest probability, you actually get new. Right? You don't get Pennsylvania, you get new. Right? So this is a funny thing. So you can't. It turns out you can't always select the best scoring token at each time step, because that basically amounts to greedy search, which is suboptimal, right? So then what you do is beam search, but then that's getting us to a different topic, which is not which we have limited time for. So, but anyways, there are different ways to decode the probability distribution that comes out of each time step, and then beam search is always a good thing to do. And then there are other things, um, the possible the popular choices are top K and top P sampling. So top K sampling basically means that I'm gonna take the top 5 scoring tokens, and then I'm gonna choose one of them randomly. Okay, so that would gives you some randomization that will hopefully make these language models more interesting. By the way, all these options, if you use any Hugging Face model, these are like available as parameters. You can just read the documentation and pass in the appropriate parameters to achieve what I described. So the top K sampling is I'm going to take the top 5 scoring, no matter how different they are. Maybe one of them is like 0.9 and the other 4 is just like 0.01. But then no matter what, choose the top 5 scoring candidates and then choose one of them. And top P sampling is I'm going to take the top P, the top so many candidates that have their probability sum up to a certain p-value. So let's say I want as many candidates. I don't care how many, but I want as many candidates such that their probability sum up to 0.5, and then I'm gonna sample from there. Okay. So, oh, and by the way, when it's a top K sampling, it might not be that they want to sample from the top five uniformly. They might just sample from the top five with their, they want to sample from the top K with their probabilities. So let's say if the top K were like the probability distribution, let's say if it was zero point 0.9, and then 0.01, 0.01, 0.01, then the 0.9 will actually be selected with the greatest probability because it's also sampled by that probability. Okay, it's just the range of candidates that the algorithm can choose to sample from that differs between top K and top P. But then these are different ways of sampling from probability distributions. Okay, so this is how you generate an output from a recurrent model, from an encoder decoder model like this. Because remember, the example we have here for the decoder is basically an LSTM, which is basically an RNN with some gating added, right? So this should be pretty understandable. Okay. So the forward pass is you input the source and target sequences, and then the output, as I said, is a probability distribution. It's not just one sequence. The output is a probability distribution. It's up to you how to interpret and decode and sample from that distribution, right? The output is not a sequence. That is a common misunderstanding. The output is a distribution. Simple set. And then, I think in the lecture, the professor talked about how you can compute the loss between the desired sequence and the distribution that it outputs as, you can basically take the cross entropy between the output distribution and the target sequence, right? So there are different ways of taking the loss between a distribution and a target sequence, right? So here, this is pretty self-explanatory. If you apply SGD, you may randomly sample words from the output, but then there are other ways to sample the output, as I talked about. So this is pretty self-explanatory. We don't need to spend time here. It's literally you need to apply the loss at each time step between either the distribution or some other output to sample from it, and you need to take the loss between that output and the target sequence that you have as the ground truth. Okay, so as I said, encoder decoder is called encoder decoder because the encoder condenses the entire input sequence to a single hidden state, right? Let's just, for simplicity, let's just assume it's a single vector, right? It's a very high dimensional vector, but it's a single vector. And there are fancy ways of projecting a higher dimensional vector to a two-dimensional space, right? Because we can only read two-dimensional diagrams. And it turns out that this architecture is wildly successful, at least by a couple of years ago standards. I mean, now we have ChatGPT, but then nobody knows how it works. But then this has been around for a while, and it's been really successful. And so what you notice is that different input sequences actually get mapped to the hidden state space with some structure. Okay, so similar inputs, as we come to know, similar inputs actually get mapped to similar locations in the dimensional space, right? So if you look at these diagrams here, John respects Mary, John is in love with Mary, John admires Mary. These three inputs they get mapped to the lower left corner. Whereas Mary respects John, Mary is in love with John, Mary admires John. These three things, so these sentences are a different cluster because they're not the same thing. Like John loves Mary is not the same thing as Mary loves John, right? But then, so each cluster is close to itself, and then these two clusters, they share a spatial relationship that is similar to what we observe when we say, she was given a card by me and I was given a card by her. So these things, they share the same spatial relation with the pairs, John loves Mary and Mary loves John, right? So when we look at these diagrams, we notice that there is some kind of structure created in well-trained encoder-decoder architectures. So this is an interesting thing that we know about. So remember how earlier I talked about word-to-vec, which is an interesting instance of word embeddings. So this same thing happens with word-to-vec, right? So each word will be turned into a vector by that algorithm, and then that vector is also in the very high dimensional space, but can be projected to two-dimensional space, right? So what you find is that if you take the vector for king and you subtract the vector for man and add in the vector for woman, then you get the vector for queen, which speaks to how semantic that these encoding methods are, which is pretty interesting. Okay, so naturally there are problems with this framework, and the most common, the most straightforward, like the immediate problem you can notice is that this one node is overloaded with information, right? So like there's if you have a vector with two dimensions, right? Let's just say two dimensions. Two dimension is not a high dimensional vector, but then you have two dimensions. There is limited information that you can encode in that two-dimensional vector, right? There's not a lot of information. And so you can make this vector arbitrarily high dimensional, but then that's also going to make it a lot more hard to train, right? And also, if you have longer and longer sequences, and exponentially, there's essentially infinitely many possible input sequences that you could encode, and there is no way that you would expect that a finitely many dimensional vector can encode all that information in all possible, essentially unlimited collection of possible input sequences, right? So this one node is overloaded with information, and this becomes the problem with the encoder-decoder framework. So the idea is that the hidden state, so remember when we were on the earlier slide, the hidden state gets produced every time step, right? So in here, the orange box, it's there for every time step. And the idea is that, okay, if the one hidden state after the entire pass of the encoder is overloaded, then we might just use a collection of different hidden states for decoding, right? So if we are decoding the first time step output, which is ich, right? So you know that ich in German means I in English. So maybe in that time step, we should use the hidden state at the first time step of the encoder more, because the first time step of the encoder, we're just dealing with I here, and the hidden state has more relevant semantic information, right? So the idea is that since that one node is overloaded, we might just, for each time step of the output, we might just use a collection of input hidden states to do the decoding rather than relying on the last time step, right? Okay, so
Yeah. So, am I audible? Audible? Okay. So, as Josh mentioned, so we saw that in the previous encoder decoder model, all the combined information from all my previous states were overloaded on the last hidden state. But just to overcome that, there was a modification to that model where we used the average of all the hidden states of the encoder and then used it to feed into the decoder. But what's the problem here? The main problem here is all the weights are, all the words are weighted equally. So which is a problem. Like we are trying to say that apple and itch are at the same weight as I and apple. So as a modification to this architecture, uh, we use a weighted combination. So in weighted combination, what we're trying to do is we're taking all the outputs of the hidden layer of the encoder, and then we are computing weights through backpropagation, and then using all of these weighted combination of all my encoder hidden states to feed it into the decoder. So in this way, Apple, whenever there is a decoding of apple, there's a high importance or high weightage that is given to the word apple rather than I ate or end of sentence. So this is the main idea behind what attention is. We take the weighted combination of all the encoder outputs and use it to feed it to the decoder, and along with the previous hidden state of the previous prediction of the decoder. So in this way we are giving, sorry, so in this way we are giving more weightage to the word that is more prominent. So here the weights are dynamically computed, and through backpropagation of divergence, the loss that is calculated between the divergence of the actual ground truth and the predicted output, the gradients are backpropagated and the weights are calculated for the encoder. Okay. So here, when we are calculating this weights, we are calculating the weights with respect to something called as the energy function. So energy function takes in the hidden state as well as the decoder's previous output, and the function g. Like in the upcoming slides, I'll tell you what the function g can be used as. And for the energy function, we are basically computing a softmax. Here, as an intuition, you can think, you should not think of softmax as a probability distribution. Rather, it is more of a relative weightage of a given word with respect to all the other words in that given sequence. So, as I mentioned, the G function that is used for computation of the energy can just be a dot product between my hidden state and the decoder's previous state, or it could be or we could have a transformation between my previous hidden state and the decoder's previous hidden state. Uh, so WG is a learned parameter. Uh, the first one is useful when both the dimensions of your encoder hidden state and your decoder's previous state have the same dimensions. But if there is a dimension mismatch, then we could have a transformation WG. Similarly, there are other two functions like an MLP can be used between these two to find the correspondence between my decoder's previous hidden state and my encoder's output. Again, as I mentioned, usually by default, most of us use the dot cross attention, dot product cross attention, which is the first one, where we just multiply the encoder's hidden state along with the previous decoder's prediction, and then we compute the weights. So these weights are then multiplied to the encoder's output and then fed into the decoder network. So for decoding, we know that in the decoder we need something called as the S minus 1, which is used as the initial hidden state. What are various options where we can, what are the various options that we can have for our first hidden state? So one is simplest is having it as all zeros, which is not a good thing. And secondly, we can have that hidden state as a learnable parameter, or we could alternatively just use the last output of the encoder and use it as the initialization for my decoder. Again, if there's any mismatch or something, then we can find a transformation between them. So S minus 1 will be some weights times my last encoder hidden output. And then once we have the initial state, so as you saw in the previous slide, we get the weighted combination of my H and S, and we compute the context. That context is fed along with the previous prediction from the decoder, which can be used for predicting the current word at this current time step. So this process continues until there's an end of sequence symbol that is produced. So one modification to this architecture was introducing query, key and value. So basically in this architecture, they split the hidden states into a key and a value vector. Similarly for the S minus 1, that is nothing but your decoder's hidden state is turned into a query value. So basically decoder query is a characteristic of the decoder and key and values are characteristics of the encoder. The decoder sends out a query to the encoder. The using the key, the encoder would return a value. So how these keys and values are computed are, so taking the hidden vector, it's multiplied by some weights. So these weights are actually learned parameters. So all the weights are same, like all the red vectors have the same, they have the same weights, and green vector also has the same weights. So the energy function, as I said, here in this modification will take the query and it will take the key, find the dot product between them, and then we apply a softmax where we get the uh, weights of computation. Uh, and then using that weights, we multiply it to the value. So previously we multiplied the weights to the hidden vector itself, but here in this architecture, we are multiplying the weights to the values that are produced from these encoder hidden states. So mainly, main advantage of this is it's these query and keys are like which portion of the input should I give more attention to. Uh, like say for example, when I'm predicting apple or something, then I give maximum weight to apple rather than the other words that are present in the vocabulary. So what basically does the attention module learn? So as I mentioned, we have the weights, the query and the key are generated by multiplying the hidden state by some transformation to form the key and the value. So we have learnable parameters for the query weights matrix, and then the key weights matrix, and then the value matrix. And after this, there was another modification to the same architecture, which is called as the multi-head attention. So previous one was a single head attention where you had just one query, key and value for all the hidden states. But here we have subset of queries, keys and values for each of the hidden state of the encoder and the decoder architecture. So my intuition on this is like one attention head would focus on uh, attending to certain kind of context or something. So say for example, one could pay attention to the relative positions between the words. One attention module could pay attention to the punctuations that are present in the sentence or something. So we are basically taking all the attention vectors that are present there, concatenating it and then passing it into the decoder for decoding it. So this is the extension of multi-head attention. So one trick, like as Prof would have mentioned in the lectures, is teacher forcing. So what is basically teacher forcing? It's basically a process where you're cheating the architecture when you're trying to initially train the architecture. So initially when you're training it, we know that the decoder will take inputs from the encoder as well as the previous decoding of the decoder. So initially, since your network hasn't learned much, it will have some erroneous predictions. So once you predict an erroneous prediction in time step t0, that will be continued and it will get carried on to all the other time steps. So just to avoid this, when we are initially training the network, we use a teacher forcing of 100%, where we are feeding the actual ground truth as the previous input here in the decoder, like below, along with the encoder outputs, so that we get correct prediction and the network learns better. And as the training progresses and once we get a good validation accuracy, we keep reducing the teacher forcing rate, and keep passing the previous prediction into this next timestamp.
We're increasing the teacher forcing as we train.
We are decreasing it. At initially, the teacher forcing rate is 1, which is 100%, or it could not, you cannot use 100%, maybe 0.95. So your ground truth is being fed initially. As your model starts performing well, as you get better accuracy, you keep reducing the teacher forcing rate, so that the previous prediction is being fed rather than the ground truth itself. So as your training proceeds and you get a good validation accuracy, you reduce the teacher forcing rate, and at a point you actually stop. So again, for back propagation, we basically compute the divergence between our target output and the output distributions, and then we back propagate all the derivatives through the network. So the teacher forcing rate is like a parameter. So it's basically a probability with which you feed in your ground truth or your previous prediction. So this is an attention map. So typically an attention map should look like a diagonal, like this. This basically gives the correspondence or the weights where any given word is concentrating while it's predicting these outputs. So say for example, when we are predicting the word agreement, it's accord. So the uh, white color represents like maximum attention, and the gray color depicts less and less attention that is given to that corresponding word in translation. So this you are going to encounter in your homework 4P2, where you will have this attention map. So yeah, it will be covered in the recitation, but just make sure that your attention map looks like a diagonal when you're training it. So this is some example where in a sentiment analysis, when the network is predicting some sentiments, I'm just highlighting which portion of the sentence did the network actually pay more attention to while predicting a given sentiment. So attention models can also be used in image captioning. So you can see here, given an image and you're trying to predict what the image actually does is, when you actually back propagate and check where the model is actually paying more attention to, you can see that it's like in the first one, a woman is throwing a frisbee. So frisbee is there. So it is paying most attention to that frisbee region. Similarly, for the dog, it's actually concentrating more on the region where the dog's face is present. And similarly for all the other images. So LAS stands for Listen, Attend and Spell. So this was a paper by Google that was released in the year 2015. This is the model that you're going to be using in homework for P2 for sequence to sequence prediction. In this, basically, they're using for your embeddings rather than using your conv layers. Like for your homework 3P2, I think most of you would have started doing conv layers for embedding. So rather than that, we have something called as a PB-LSTM, where since our input sequence MFCC is a large sequence, we want to downsample it. So in order to reduce downsample them and without losing much information, we are actually projecting it into higher dimension space. So here basically we feed the inputs, and at each time step we are concatenating two time steps to form one output to that LSTM. So the LSTM is bidirectional here. So say for example I had 128 timestamps here, I would reduce it to 64 and then eventually 32 there. Uh, when we are actually reshaping it, there are various strategies. One is you're basically reducing the time steps, but you can actually concatenate all your feature dimensions. So your feature dimensions increases by a factor of 2, or you can explore various other pooling metrics like average pooling, etc. But we wouldn't want to do an average pooling because we don't want to lose information. So suggestion is to have the features concatenated one behind the other. So according to the paper, yeah. So before that, if we have order even sequence, make sure that we're padding it or we're truncating it. I would suggest padding it because we wouldn't want to lose information. And then we have bi-LSTM, the pyramidal bi-LSTM, and then we reduce the length by a factor of 8 as we proceed. So this is going to give us the encoder's output. The encoder here is called as the listener. Then there's an attention module, and then there's a speller. Speller is the decoder in this paper. So this is the decoder. So this is similar to what we saw previously. In here as well, we are using RNNs or LSTMs are being used here. You can see that Y2, Y3 and YS minus 1 are used, which is for the teacher forcing, where we are feeding the ground truth in the initial parts of the training, and the context is computed from the previous state and fed on to the next time step. Here the output is nothing but an MLP plus softmax, which gives a probability distribution over the characters that are present, or it could also be a word based distribution, but the paper does a character distribution. And there's something called as online beam search here, because we are selecting the words like at each time step the previous prediction is fed into this next time step. So we want something that is like an online decoding of the characters given these many predictions. Like if you consider at time step y4, so given this sentence, what is the most probable word or character that could occur at time step y5 is calculated using the beam search, and then that is being fed at time step 5. So this is about decoder of the LAS, and attention can be single head attention or multi-head attention that is present in between them. Yeah, this is about it. Any questions?
Are these designs like specifically for certain tasks? What tasks or is this one for?
This is for sequence to sequence prediction. So in your homework for P2, you have speech to text translation. So you would be using this LAS there.